So in problem 20, we have these two vectors, v1, which is 1, 1, negative 2, and v2, which is negative 2, 3, 0. And we want to describe the span of v1 and v2 geometrically. So the span of a set of vectors is the set of all possible linear combinations of those vectors. So the span of a set of vectors is all the linear combinations of v1 and v2. The span of a set of vectors is all possible linear combinations of v1 and v2. That's for every real number, everything that looks like x1 v1 and x2 v2. So that's everything, all the x1 v1 plus x2 v2. So it's all the possible x1 v1, x2 v2. Those are linear combinations. One thing to note about a span, which will get reinforced later, is that this includes 0 v1 plus 0 v2. So the span of a set of vectors always contains the origin. So that's an important thing to note. The other thing important to note about the span of a set of vectors is where this set of vectors lives. Notice that each of these vectors, v1 and v2, have 3 entries in them. So v1 and v2 are vectors in R3. So the span of v1 and v2 is going to be sitting in R3. That's 3-dimensional space. Since there are 2 vectors, and the 2 vectors don't lie on the same line, we're going to get 2 vectors going in different directions, and then all combinations will make a plane. So those are the elements that we need to include in our description. So first, we'll notice that the vectors are in R3. So first, we'll notice that the vectors are in R3. The vectors are in R3, that is 3-dimensional space. So the span of v1 and v2, the span of v1 and v2 is in R3. The span of a set of vectors will always go through the origin. So all the x1, v1, x2, v2, including 0 v1 plus 0 v2, which is the 0 vector. So the span always contains the origin. So we get all the v1, v2, so including the origin. And there are 2 vectors that are not collinear. The 2 vectors are not on the same line. So the vectors are not collinear. The vectors are not collinear, so we have 2 actual distinct vectors. These vectors are linearly independent. That's introducing language from 1.7, future knowledge. The vectors are not collinear, and there are 2 of them, so the span of v1, v2 is a plane. Pick a plane because there's 2 linearly independent vectors, so we get a 2-dimensional span. The span is 2-dimensional, so we have 2 vectors. So the span of v1 and v2 geometrically is a plane through the origin in R3. It's a plane in R3 through the origin. So span v1, v2 is a plane in R3 containing the origin. The span of V1, V2 is a plane because there are two linearly independent vectors. In R3, because the vectors have 3 entries each, through the origin, because the span will include the 0 vector. 3 elements that we need to point out. Any questions? For those of you looking into the future, you're not supposed to look into the future, but for those of you looking into the future, we would say that the span of V1 and V2 is a 2-dimensional subspace of R3. And V1 and V2 form a basis for the 2-dimensional subspace of R3. I should just write that down. That's where we're headed anyway. Since V1 and V2 are linearly independent vectors, V1, V2 is a basis for a 2-dimensional subspace of R3. This set of vectors is a basis for a 2-dimensional subspace of R3. That means this subspace is a plane containing the origin in R3. That means this space is very much a copy of R2, although not exactly R2. We would say it's isomorphic to R2. Right. Any questions? Ooh, fancy language from the future. It's a basis for a 2-dimensional subspace of R3 that's isomorphic to R2, but not equal to R2. Got to introduce different kinds of equals. Any other questions from homework 1.3? How are we doing? So I see 4, 8, and 12. So we got something against multiples of 4. I get it. So in exercise 3 and 4, we have some vectors, U and V as an exercise 2, and we want to draw these on a graph. So let's take a look at these 2 vectors. Let's see, 8 and 12. Okay, 4 and 8 are both geometric. So let's take a look at 4 first. We've got these 2 vectors. U is 3, 2. That's bad grammar. U are 3, 2, and V is 2, negative 1. So if we draw a picture of these vectors, make sure I'm in focus. If we draw a picture of these vectors, 3, 2, and 2, negative 1, what we're going to find is that we're creating a different grid on R2. So if we think about R2, normally we draw R2 thus, with a y-axis and an x-axis. And the normal grid for R2, with our x and y, is just a bunch of squares. So we count 1, 2, 3, 4, and then negative 1, negative 2, negative 3, negative 4. 1, 2, 3, 4, negative 1, negative 2, negative 3, negative 4. So I'm just drawing an x and x1 and x2 axis, a regular Cartesian coordinates, and the normal grid on Cartesian coordinates. What we're going to do is we're going to, instead of dividing up this plane into little squares like we have here, we're going to break it up into a parallelogram grid where U is 3, 2. So I'm going to draw that one. U is 3, 2. There's the vector U. And the vector V is 2, negative 1. There's the vector 2, negative 1. There's the vector U, and here's the vector V, and then I drew it too small for me to draw anything else. So what these two vectors do, notice first that they're not collinear, so they are linearly, we would say these are linearly independent vectors because there's only two of them, and one of them is not a multiple of the other. So we actually have two different directions. Each vector provides different information. Now, what we've done is broken up the Cartesian, the two-dimensional plane, R2, into a new grid. So I can look at U, and then 2U is just going to be another copy of U out here, and then 3U will be another copy of U out here, and negative U will be, oops, I didn't go far enough on that one, will be another copy of U going in the other direction. So we're creating a new grid. So V has another copy of V going this way, and we have two new axes, a U axis and a V axis. So we just have this new graph paper where instead of multiples of 1, 0 and 0, 1, we have multiples of 3, 2 and 2, negative 1. So if I wanted to draw the graph of 2U plus V, I would go 2U and then plus V. And so that would be this vector here. The green vector would be at the connecting the two ends of the parallelogram. So 2U plus V. So that's what we're talking about geometrically. We look at we put the two vectors U and V, and then we make a parallel copy of U at the end of V, and a parallel copy of V at the end of U, creating a parallelogram. Then the sum of those vectors will be the diagonal of the parallelogram. So the sum of vectors is going to be the diagonal of a parallelogram. The sum of vectors is the diagonal of a parallelogram. The sum of vectors is going to be the diagonal of a parallelogram. That's the concept. One level above that, we want to view 3, 2, and 2, negative 1 as an alternate graph paper, an alternate grid, I should say, on R2. So think of U and V as a basis for alternate graph paper, alternate grid of R2. It's a different way of describing R2. Every point on R2 can be written in terms of U and V, and it would look very different than how we normally write coordinates. Any questions? So U and V, since that we can cover everything in R2 with U and V, we have another basis for R2. So going one step further, the standard basis for R2 is the vectors 1, 0 and 0, 1. This is the standard basis because it's really easy to write everything in terms of the vectors 1, 0, and 0, 1. 3, 2 is going to be 3 of the first one plus 2 of the second one. That's why it's our favorite. All right, problem 8. We do kind of the same thing, only we have the picture and we have to go backwards. Yeah, we just want to write everything in terms of u and v. So if we look at the vector x, it looks like we have to go 2v and then minus 2u because it's on that set of graph paper. That's all we need to do. Problem 12 asks a different question. In problem 12, I'll write down the vectors. We want to say determine if B is a linear combination of A1, A2, and A3. So I'm going to write those vectors down. A1, I'm going to try to write them down neatly though. A1 is 1, 0, 1. A2 is negative 2, 3, negative 2. A3 is negative 6, 7, 5. And B is 11, negative 5, 9. And we want to determine if B is a linear combination of A1, A2, and A3. So the initially framed question, is B a linear combination of A1, A2, and A3? Is B a linear combination of A1, A2, and A3? I want to write down some, oh, this is a question. I want to write down some alternate formulations of this exact same question. So we want to determine if B is a linear combination of A1, A2, and A3. We could ask this question equivalently by saying, is B in the span of A1, A2, and A3? Because the span of A1, A2, and A3 is the set of all linear combinations of A1, A2, and A3. And we're just asking if B is one of those linear combinations. The way we determine this is through a vector equation. So we want to say equivalently, is x1a1 plus x2a2 plus x3a3 a generic linear combination of a1, a2, and a3 equals B? Is this vector equation consistent? So we've taken a question about linear combinations, translated into a question about a vector equation, which means we are now able to proceed onto our augmented matrix, then the reduced row echelon form. Any questions? So this gets into this question, determining if this matrix equation, this vector equation is consistent. That gets us into an augmented matrix. So we're going to look at the reduced row echelon form of, by columns, this augmented matrix. 1, 0, 1, negative 2, 3, negative 2, negative 6, 7, 5, and then 11, negative 5, 9. I want to look at this augmented matrix and find its reduced row echelon form. I'm going to perform some row operations by hand, so give me a minute to perform some row operations by hand. I'm totally just going to do this in my mind, and let's see. So 1, negative 2, negative 6, 11, open, and then 0, 3, 7, negative 5. Close that one, open the next one, and then 1, negative 2, 5, 9, close that one, and close the matrix, and then close the command and get rid of the extra stuff, and then check. Did I write everything down correctly? Let's see, 1, negative 2, negative 6, 11, 0, 3, 7, negative 5, 1, negative 2, 5, 9. I'm going to check it against 1, negative 2, negative 6, 11, 0, 3, 7, negative 5, 1, negative 2, 5, 9. So here I am writing stuff down. And so what we get is we do not have a pivot in the rightmost column of this augmented matrix. Let's see. We do not have a pivot in the rightmost column of this augmented matrix. Therefore, we can say the vector equation is consistent. Therefore, B is a linear combination of those vectors, A1, A2, and A3. So let's write down the reduced echelon form. So this is what we're going to get all our conclusions from by columns: 1, 0, 0, 0, 1, 0, 0, 0, 1, and then this 245 over 33, then negative 41 over 33, then negative 2 over 11. So the rightmost column of the augmented matrix is not a pivot column. I didn't plan this out very good. See, I'm all out of space down here at the bottom. So an arrow. So we can see that the rightmost column of the augmented matrix is not a pivot column. We could also say there is not a pivot in the rightmost column of the augmented matrix. Dangerous to say it that way, because some of you will say there is no pivot, and then all of a sudden you'll start using that language and you'll write something wrong. The rightmost column of the augmented matrix is not a pivot column. Therefore, the vector equation x1a1 plus x2a2 plus x3a3 equals b is consistent. The vector equation is consistent. Moreover, we can see what the solution is. We can see that b, x1 is equal to 245 over 33 times a1 minus 41 over 33 a2 minus 2 over 11 a3. It's consistent, and since there are no free variables, this equation has a unique solution. That wasn't important. We just wanted to know if it was consistent or not. Moreover, the equation has a unique solution. Because there are no free variables. So we get a consistent equation, and therefore B is a linear combination of the vectors A1 and A2 and A3. Therefore, B is a linear combination of A1, A2, and A3. Specifically, this linear combination, 245 over 33 A1 minus 41 over 33 A2 minus 2/11 A3. Specifically, it's that combination. It's way more important to be able to do to reduce a matrix by calculator. Doing it by calculator is not important in your future career. Doing it by hand is not important in your future career. Finding the reducer echelon form of a matrix is going to be, in actual situations, finding the reducer echelon form of a matrix is going to take way too much computing power. We're going to have to do something else. It's not about your future careers. That's kind of an important thing to remember. We are way too early in your educational journey to be talking about what you're going to be doing in your future career. But it's a good question. I want you to do your row operations by calculator. I want you to be able to do them by hand. I want you to understand what the process is. But when I ask you to find the reduced echelon form of a matrix, use your machine to do it. Whenever you can. If I really want you to do operations by hand, I'll just replace some of the real numbers with constants like h and k. Oh, there's another conclusion that we can make. Since B is a linear combination of A1, A2, and A3, we'd say therefore, B is in the span of A1, A2, and A3. Any questions? All right. Any other questions on 1.3?
21.
Which one? I couldn't hear you. Just type it. 21. So in 21, we want to show that HK is in the span of U and V for all HK. So we have these two vectors. So U is 2, -1, and V is 2, 1. And our task is to show that HK is in the span of U. I spelled U very wrong. I spelled it with 2 U's, a double U. I want to show that HK is in the span of UV for all H and K. That is, I need to translate this into an equation. So that is, show that x1 times U plus x2 times V equals HK is consistent for all H and K. Need to translate this question about span into a question about a vector equation so that we can get ourselves into an augmented matrix. So we'll write the augmented matrix by columns, 2, -1, then 2, 1, and then HK. And then what we're going to see is that we do not have a pivot in the rightmost column of this augmented matrix. So you're going to perform row operations, and you're going to show you're going to show that there is a pivot. There is not a pivot in the rightmost column of this augmented matrix. So you just take this augmented matrix and do some row operations, and you'll find that there are pivots in the first row, first column, and the second row, second column. We're not going to have a pivot there because we're not going to be able to, there's going to be a constant here, a non-zero constant here. You're going to you can switch them to get a +1 here. Then you do the first row, or you do whatever your operation is, half the first row plus the second row. It doesn't zero this out. This becomes a 2. We'll divide this by 2. There's a pivot in the first row, first column, second row, second column. There can't be a pivot in this column. because there's only one pivot per row. And if there's a pivot in the second column, there's not going to be a pivot in the third column. Any questions? Incidentally, as the further we go, the more that more knowledge about vectors we accumulate, the less we have to do this kind of work. In this case, we can see that there are two vectors, and they're in R2, and they're not collinear, so they're linearly independent. So we're going to get a two-dimensional subspace of R2, and that's all of R2. And so HK, we can always write HK in terms of U and V. We just want to pile some more stuff on. The reason that I point that out is that as we go through problems and concepts in this class, we need to get away from the thinking that got you to this point in your math class, where you can just look at an example and learn that one thing, and then when you see a problem on a test, you say, oh, I'll copy that one example. That's how math worked for so long, and not anymore. Some of you are still trying to, I could see in your quiz work, some of you are still trying to just kind of copy the things that happened that I did to get at the answer. You said, oh, this one looks like when he was talking about that one example, so I'll just do that one example with these new numbers. And that is going to be harmful as you're trying to move forward understanding in this class. In this class, everything is connected, and you have to think about all the things all the time. That's the only way that you're going to be able to make those kinds of connections. It's not the only way. It's the most efficient way to start making those kinds of connections. Any questions? Comments? All right, let's pause the video, and we can set ourselves up for looking at homework 1.4.